Good day, students. On this clip, we're going to be going over an example on how to calculate the work done by a variable force over a space curve. Okay. All right. So let's write down the question that we're going to be working on. So the instructions are as follows: find the work done, by a variable force which is given by the vector F equals x plus y in the I direction. Let me just put I hat plus y plus z in the j direction plus x minus z in the k direction, k hat, over the curve. This is a space curve over the curve. R of t equals t squared I hat in the I direction plus t in the j direction plus t to the third k hat in the k direction. Assuming that we're going to go from 0, the time starts from 0 all the way to 1. Okay? And then let's see we're going to move from position 0, 0, 0 all the way to position 1, 1, 1. Okay? So this is a three-dimensional space curve. We're going to see the work done by this force in moving a particle along this path, starting from 0, 0, 0 all the way to 1, 1, 1. Okay? Alright, so before we start, just a little background. Remember a basic formula for force on uniform force in a uniform path. Remember the work. Oh, good. Okay, change this. Sorry about this. Remember the formula for work done is basically work is force times distance, right? Force times distance. Let's call it S. Alright? So what if we have a variable force and a variable path? We're going to have to use a line integral to basically compute what the work is. Okay, so if you have a variable force on the curved path, the work done is going to be integral over the starting time to the end time of the force as a vector dotted with the position, the RDT. We're going to be looking at the path instantaneously, the RDT. Okay, so basically this is how you compute the RDT, the work done. Okay, the RDT times dt. Okay, so in the formula we're going to be using today, we are going to express f. We're going to evaluate f on the curve, and then we're going to compute the RDT, and then we're then going to evaluate the integral from 0 to 1 of the dot product of the force evaluated on the curve and the derivative of the position vector. Okay? Alright, so let's go ahead and do it. Let's start with the first step. Remember, this is just your basic force times distance formula. Okay, nothing too complicated about that. Alright, so step 1, what we're going to do is we're going to evaluate the variable force, evaluate F on the curve R. Okay, on the curve R. So how do we do that? Well, what we're going to do is we're just going to keep track of what the x, y, and z values are along the position function, and we're going to substitute that into the force vector. All right. So if you take a look at r, let's rewrite r down here. R of t is t squared. I want to use the vector notation using coordinates, so I can write it like that: angular bracket t squared comma t comma t to the third. This is the same as that, only that I don't like writing this I hat, j hat, k hat over and over again, so I can write it using this coordinate notation. Okay, so you can see that this is the x component, this is the y component, and this is the z component. All right, So basically x is t squared, y is t, and z is t to the third. So what am I going to do with that? I'm going to plug in these respective components of this vector, the position, into f. All right, into f over there. All right, so let's go ahead and do that. So f, I'm going to rewrite f before I make the substitution so that nobody gets confused. Okay, so f is a vector. T is f of x, y, z is going to be a function of t in a minute after I do the substitution. So f is basically using the coordinate notation, so I don't have to write I, j, and k. It's x plus y, comma, this is for the x, the I or the x direction, and then for the j direction is y plus z, and then for the z direction it's x minus z. Alright? This vector is exactly the same as the vector in the question, x plus y, y plus z, and x minus z. Alright, so what we're going to do is for x, for anywhere we see x, we're going to plug in t squared. Anywhere we see y, we're going to plug in t. And we'll have z, we're going to plug in t to the third in the variable force vector. Okay? So f of t now is going to become x plus y is going to be t squared plus t, because that's x and that's y. And then y plus z is going to be t plus t to the third. And then x minus z is going to be t squared minus t to the third. Okay? So there goes your f evaluated on the curve. Alright, now that we have f evaluated on the curve, we're going to find what we're dotting this variable force vector with. Okay, so step 2, we're going to find instantaneous rate of change of position with respect to time, the RDT. Okay, we know that the position function using my coordinate notation for vectors is t squared, t to the third. So the RDT, we're just going to do term by term differentiation. The RDT is simply going to be 2t, comma, derivative of t is just 1, derivative of t to the third is 3t squared. Okay, so there goes your dRdt. Alright, now that we have the derivative of our position vector, we're going to now find the dot product before we evaluate the line integral. Okay, so we're going to find the dot product of the f evaluated along the position function with the instantaneous rate of change of position, the RDT. So we're going to find the dot product of f and the RDT. Okay, remember these two are vectors, but our result is going to be a scalar function. Okay, so when we dot it, we're going to have we're dotting t squared plus t, comma t plus t to the third, comma t squared minus t to the third. This is f. Okay, we're going to dot it with the RDT that we derived up here by differentiating the position function. It's going to be dotted with t squared, comma t to the third. All right, so let's evaluate the dot product. We just multiply the x's. So we're gonna have oh, okay, wait a minute, I made a mistake. The RDT is 2t1 and 3t squared, so let me correct that real quick. So we're supposed to plug in the RDT, so the RDT is basically 2t, comma 1, comma 3t squared. Alright, so let's go ahead and do the dot product. So we're going to multiply this times this. So we have 2t multiplied by t squared plus t plus 1 multiplied by t plus t to the third, and then plus 3t squared multiplied by t squared minus t to the third. Okay, so we're just basically multiplying the x's together to get this, the y's multiply together to get the middle term, and then the z's, we multiply them together to get the last one. Okay, so that's your basic arithmetic for procedure for finding dot products. Alright, so we distribute this, we have 2t to the third plus 2t squared plus t to the third plus 3t to the fourth minus 3t to the 5th power. Okay, now we just found the dot product of f dot drdt. Well, let's see. Let's rewrite this in standard form. Okay, so basically the dot product f dot dr dt is equal to negative 3t to the 5th plus 3t to the 4th plus t to the 3rd. Oh wait, we can combine this and this together. And we combine t to the 3rd plus 2t to the 3rd. We're going to have 3t to the 3rd. Okay, so we have 3t to the 3rd, 3t to the 3rd, and then 2t squared is on its own plus 2t squared plus t. Okay, so there goes the dot product of your variable vector force and the derivative of the position function. Okay, now that we found the RDT, step 4, which is the final step, we're going to evaluate the integral, the integral from A to B, which is the starting t position, to the ending t position of f dot dr dt with respect to dt. Okay, so this is the final integral we're going to evaluate. Since we're starting from 0 to 1, what we're simply going to be evaluating here is the integral, the definite integral from 0 to 1 of this dot product we arrived at with, which is negative 3t to the 5th plus 3t to the 4th plus 3t to the 3rd plus 2t squared plus t. Alright, evaluate this whole thing, dt. Okay, so using the laws of integration, we're just going to use the power rule for integration to integrate all of these terms. Okay, so if we do that, we're going to have negative 3t to the 6th over 6 plus 3t to the 5th over 5 plus 3t to the 4th over 4 plus 2t to the 3rd over 3 plus t squared over 2. Now this entire indefinite integral, we're going to be evaluating it from 0 to 1. Okay, so we can see that if I plug in 0, so the whole term, I'm going to end up with 0. All that matters here is what happens when I substitute 1 for my t. Okay, alright, so using the fundamental theorem of calculus, I'm going to plug in 1 into everything. So I'm going to have, for the 1, I'm going to have negative 3 times 1 to the 6th over 6 plus 3 times 1 to the 5th over 5 plus 3 times 1 to the 4th over 4 plus 2 times 1 to the 3rd over 3 plus 1 squared over 2, and then subtract that from what you get when you plug in 0. Since every term has a t there, when you plug in 0, you're just going to have 0. Alright, and that's inconsequential. Alright, when we simplify this, we're going to have negative 3 over 6 plus 3 over 5 plus 3 over 4 plus 2/3 plus 1/2. Okay? Alright, this reduces to negative 1/2, so if the first and the last terms cancel out, you can cancel that out. If you find the LCD of these three values, these three numbers, 5, 4, and 3, the LCD is basically 60, so to get 60 out of here, I'll multiply this by 12, multiply this by 12, multiply this by 15, and I'll multiply that by 20. Okay? Alright, so working on my fractions, I'm going to end up with 36 over 60 plus 45 over 60 plus 40 over 60. Okay, if I add all the numerators together, I'll end up with 121 over 60. And there goes the work done by this variable force from t equals 0 to t equals 1 along the position function that was given earlier. Okay? So thanks so much for taking the time to watch this video. Please feel free to subscribe to my videos by clicking the icon up here. More videos can be found on mathjoseph.com. Thanks again and have a wonderful day.